Hello again. Tonight we're going to talk about affecting photon velocity, not speed, velocity. So velocity is a term, a number of things, physics, that is used as a vector metric. What that means is velocity, it's a number and a direction. So it's how fast something is going, distance over time, and a direction. In the case of physics used in astronomy, it's not just compass direction, it's three-dimensional direction, so 360 by 360. You can actually change velocity by changing either or both of speed or direction. If you want to, you can change the direction and not change the speed, and you'll have a change in velocity, but not a change in speed. You can keep the speed of light and just change the direction. Everybody knows that, a reflective surface can change the direction of light. You've changed the velocity of the light without changing the speed of light. So photons have always been perceived as elementary particles, meaning you can't decompose them into other things. At one time, atoms were thought to be that. And then we found out about protons and neutrons and electrons. And then we found out, hey, you can break a proton or a neutron apart and you can get quarks. You can get groups of up or down quarks in various flavors. And then you found that, well, the quarks like to be stuck together into these groupings, and the things that glue those together are gluons. The higher levels of energy that we have in our particle accelerators, and the more experiments we do, the more likely it is to break what we thought of as elementary particles into newer, smaller particles. And then we identify those and their energy levels and such. There have actually been experiments in colliding photons into photons. Well, photons are not directly interacting unless they get absorbed and reemitted. A photon does not directly interact with another photon. They don't repel each other and they don't attract each other. They just predominantly ignore each other. Some might say they're small enough that they don't interact with one another. They slip past one another. But there have actually been experiments. If you have a large enough flux, a large enough density of photons, and you have them all going in one direction, and you have them all phase aligned like a laser, then you can point one at the other. And now the probability of a photon directly colliding with a photon is increased above zero. It's still rare, but it's increased above zero. And when a photon collides with another photon, you get electrons and positrons. You don't get any more photons. Suffice it to say, they're looking into what is known as two-photon physics, how to get a photon to collide into another photon and the behaviors of it, the end result. If you're adept in photons and physics, you probably have heard of the photon particle wave duality. Depending upon how you're observing the photons, they can behave like a particle or a wave. And they have this duality. If you're looking at them with one kind of experiment, they'll exhibit wave effects. If you're looking at it with another kind of experiment with a different kind of sensor, they'll exhibit particle effects. So they have this duality. And they have a frequency and they have an energy level or amplitude, usually measured in electron volts, but wavelengths, frequency, they're related. You have different flavors of photons that are in different wavelengths. The high energy, very high frequency, very short wavelength, picometers to nanometers, picometer being 1,000th of a nanometer, and a nanometer being a billionth of a meter, very, very short. So you have gamma and X-ray and UV, and then it gets down to the stuff that our human eyes can see. Those are in the nanometers, those are visible. And then it gets to longer wavelengths, micrometers and millimeters, and that's in the infrared region. And then you go down even further in energy and longer in wavelength, and you get centimeters to meters. That's radio band stuff, microwaves into long wave. The amount of time it takes for a wave to propagate varies with its wavelength. So if you have a phase aligned photon and it's a very low frequency, very long wavelength, there is a given amount of time that it will take for that wave to propagate through space. That takes time. Think of it as a longer train taking longer to clear a crossing. Just remember it as long wavelength, long time, takes time. So there's this thing called refraction, and materials have something known as a refractive index. And when you pass photons through a material with a different refractive index, it will bend the light. It doesn't change the speed of light. The photon gets re-emitted in a different direction based upon the refractive index, index of refraction, index of reflection. But if you have a lens, you can dope it with materials and make it change the index of refraction and bend the light. You haven't really slowed down the light. It's still traveling at the speed of light. All it did was make it go a slightly different direction when it's traversing the material. It's not a change in speed, it's a change in direction, which is a change in velocity. So when they tell you they've changed the velocity of light, that's true, but they haven't changed the speed of light. So if they make it bend, like through a coil of fiber optic material that has got a specific index of refraction, the amount of time it takes to traverse a longer and longer coil of fiber optic versus the beam just going straight, the time it takes for the light to go through the coil is going to be longer than the time it takes for it to just go straight. What's the shortest distance between 2 points? A straight line? Yeah, okay. If we add material to the material that's traversing for color doping, we can not only change the end-to-end speed, we can also change the color or the wavelength when we bend the light. The speed is still unchanged, only directions change, but the velocity therefore is changed. There's this other concept called wavelength upconversion. And where this might be something you'd recognize is if you take two photons of a long wavelength and you combine them in a material, you can come out with a wavelength that is shorter. So two of an infrared combined together to make one of a green at roughly half the wavelength. So you take two infrared, merge them together, you get one green, which is 1/2 the nanometer wavelength of the infrared. But we have to prepare special materials. It's a crystalline matrix. Literally, you have to have the material inside the crystalline matrix interact with the two photons to make them basically align with the crystalline lattice, and therefore they get absorbed and re-emitted. And they get re-emitted at the higher energy level. So infrared becomes green. This is what laser pointers do. Your cheap laser pointer, it's actually an infrared laser that then goes through a particular crystalline material, cut at just the right angle in order for it to convert the infrared into a specific wavelength of green. That's why most of the green laser pointers are all the same nanometer value. But that up conversion is not dynamically or digitally tunable, and it requires you to custom make materials in order to get higher wavelengths. But it doesn't stop at one level. If you make a up conversion of a specific kind of crystalline material, you can boost it above green and get almost to ultraviolet. So you can start with an infrared laser, put it through the right kind of crystalline material, cut it just the right angle, and instead of getting green, you can get a very specific blue called royal blue that is very close to being ultraviolet. So up conversion, again, not changing the velocity of light, but by bending the photons and making them align along a crystalline lattice, you can get them to merge and make a shorter wavelength. So it's a way of essentially clipping an infrared wavelength down to something shorter. But the fabrication costs are expensive for the very first one you make, and then you have to make them in quantity before you can make your $30 infrared into a green laser. There's a new way for doing this. They found that there's this concept called photon truncating. It's in the realm of something called nonlinear optics, and it's where they can have materials, predominantly something called lithium niobate, that's lithium, niobium, and oxygen, into a thin film coating. And they found that when you have this particular crystalline thin film coating, through something you can transfer light through, you can run a high voltage at very low amperage, very low current, through the material, and the material will change its index of refraction. If all you want to do is bend the light, this is used in fiber optic switches in large scale data networks. But you can also use it as a shutter. If you input the right voltage, you can actually bend the light away at like 90 degrees. And so the light just becomes infrared heat and doesn't pass through. Well, they found that if you do this, you can create what is known as a light modulator. You can switch a light beam off and on at very high frequencies, and you can actually put data on top of the light beam by switching it. And then they have things called phase separators, where you can not only switch the light beam off and on, you can actually say, I want this phase of the photons to go here and the other phase to go there. So you can actually phase split things. So you can convert a otherwise non-aligned beam of photons, a flux of photons, into something that is coherent, meaning all the same phase, all the same amplitude at the same alignment time. And now you can make a very strong communication signal by modulating, clipping these pulses of coherent light. And they said, well, what if we have a long wavelength, and instead of waiting for the wave to pass through, waiting for the train to go by before we raise the crossing gates, what if we clip the train, clip the wavelength in mid wavelength? And they found that they can use very fast switching to actually take a long, like an infrared wavelength, and break it, like as if you have a strand of spaghetti and you snap it somewhere in the middle. You can break the photon. But they also found that they haven't quite got it down to a controllable state. They don't get all the right wavelengths out of it. If they do this, they wind up with a lot of different wavelengths instead of exactly where they kind of threw down the meat cleaver of the shutter. Think of it as if you had a bundle of strands of pasta and your cleaver was sharp, but it was very slow. And it went snap, 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 snap. Well, as the cleaver bends the bundle of strands of pasta, some of them will come out being longer or shorter than others because you're not cleaving it quickly enough and sharp enough. There's things you can do to improve that. Make sure all of the photon wavelengths are the same length. Make sure they're all aligned so that they all start at the same time. And then make sure your cleaving has little chance of being in the middle of things. And the best way to do that is if you know the amplitude and the wavelength of your photons, you can actually know where the sinusoidal wave crosses zero amplitude. Clip it there, but you've got to clip it fast enough. So maybe you have to go from picoseconds to femtoseconds to get that cleaver through there before any of the strands move out of alignment. And now you can actually cleave a flux of photons to a specific wavelength of your choosing. So if you can clip them under software control, then you can take a long wavelength and you can clip, 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 clip. You can take a wavelength of infrared and tune what color you want coming out, what energy level you want coming out. Emit your phase-aligned IR, clip it so fast and at the right crossing point that you get exactly the wavelength you want. And if it's a multiple of the long wavelength that you want shorter ones, you have to clip it, clip it, clip, 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 clip. So you might need multiple cleavers. Adjust it for whatever you want, whatever color you want, whatever wavelength you want at that moment in time. There's some practical applications of this. Research into photon wave truncation is increasingly interesting. They've got some insights now on how maybe to do it better under digital control. Maybe once I post this to the public via YouTube channel, they'll pick up on something. If you can use an infrared solid state laser emitter, you now have the phase coherence and the alignment down. And then if you can cleave it fast enough, maybe fractional picoseconds or femtoseconds, you might cleave it fast enough that you won't get different. But what good is that? Well, today we have these things called LEDs that we use in a lot of different things. And we have to have red, green, and blue ones in order to get the color we want through mixing. What if you could get the color you want through software selection of clipping of the wavelength? Dynamically adjust the wavelength for whatever color you want at whatever point in time. So if you can do that on a per emitter in a display, You no longer have to make different chemistries of LEDs, basically associated with what is known as the band gap of the semiconductor material to get your red, green, and blue. You can dial up whatever color you want based upon what wavelength you want. Now, instead of having displays that have red, green, and blue and multiple LEDs in the matrix, you can have all the same kind of little infrared laser emitters and just have nonlinear optic, very high speed switches on the front of them that will chop up the wavelengths for whatever color you want. There would be a significant reduction in the cost of displays, be it TVs or monitors, and you'd have a much finer color selectivity than you would with fixed red, green, and blue mixes. You could actually make colors that the human eye can't see because retinas have essentially red, green, blue, and luminance or black and white sensing. But you have to mix the colors. There's this thing in HD TVs called HD10, which is the color renditioning standard. And it has a certain number of billions of colors, but it has gaps in it. It's not contiguous. If you had something like this, you could make whatever color you wanted down to the speed of how fast you could make your nonlinear optical switch. Photon wavelength truncation. If you see it come up in a YouTube video, I won't say you heard it here first, but I just brought it to your attention and brought some things that they could probably take a look at and see if it would make things even better. But I think that's how it's going to wind up, is because they're always trying to look for how to make TVs and computer monitors cheaper, higher resolution, easier to fabricate. If you only have to fabricate one kind of emitter and it's just software that adjusts the wavelength, that really brings down the price of things. So if you didn't know about such things, lots of background information. Who doesn't know what a photon is? And then that photon-photon collisions, and then photon truncation. And what is this coherent light of which you speak? Comments? Questions?
I think it's amazing that you're thinking of applications when they're still doing all kinds of research in what light is, what photons are.
Well, years ago, I watched this James Burke series called Connections.
Yeah.
And if you see this and you see that, connect this to that and go, I have an application for that. And sometimes the two things that you're looking at don't seem to relate to one another at all. It always amazes me that science teams can have blinders. You know how your mule or even a horse can have blinders on. So just focus ahead. That's all you're going to focus on. Just focus what's ahead. And don't look to the left. Don't look to the right. Just keep on target. And a lot of science teams operate in that manner. I know I've been one that did that once back in the day, but over the years, I've learned, like, look around everywhere. Everything can be connected to everything. You may learn something about what you're trying to do from something totally unrelated. It's like I looked at photon truncation and I went, well, I see what's happening. Your meat cleaver's not going through the flux of photons, the stack of spaghetti strands, fast enough as you're pushing them through. So you're like, clip, 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 clip. You're clipping a curve, you're not clipping a straight line. I can figure that out. Clip faster. Light up the strands. Clip faster. Clip it at the point where the wave, because there is particle wave duality, where the wave goes through a zero amplitude point. So you're not clipping it on the curve, you're clipping it right at the zero crossing point. Just things to think about, guys. So if this gets out to the public and then all of a sudden you see, hey, we can now dynamically make whatever color photons we want by starting with infrared, and we just have a switch, a nonlinear optics switch that runs at the not nanosecond, not picosecond, but small numbers of femtoseconds. I won't say you heard it here first, but
We're getting down to the point where it's microscopic, atomic level things. microscopic wire is has to be controlled as
Oh
far as.
yeah, yeah. And in fact, I watched a YouTube video this week that they said the interconnects between computer processors and their cache and main memory that's on the same substrate as the computer core,
Yeah, the
they,
connections.
they, they can't use copper anymore.
No.
Copper's run out of steam. They're going to be using photons.
Oh, oh,
Yes. So they're actually going to be creating photon emitters and sensors that work at very short wavelengths of light. And they can switch that at the attosecond, which is like nano, pico, femto, atto. That's thousands of thousands of thousands of a meter. They're going to be able to push the ball down the road a little farther. So they're going to have to speed up memory arrays so that the memory arrays can keep up with the processors. The bridge to go from the processor to the memory array, copper just wasn't cutting it because copper is not a perfect conductor. Copper has infrared heat it produces. And with the quantity of electrons they're sending over these bridge interfaces from the processor to the memory is so high, it's producing a lot of waste heat, not individually, but collectively. And so to get rid of the waste heat, stop using a metal conductor, use a photon conductor.
wow.
And the best photon conductor is no conductor. So they're going to have to find a way to literally make them small enough that no particles are in between the processor and the memory. It's not that they're butted together, they are slightly separated, but the separation distance is so small, there's no particle of anything except the actual photon that can get between there.
We're fighting against nature. I think there'll be some.
Oh, they've already done that. They had to find ways to get below 8 nanometers feature sizes on integrated circuits. And that was because an electron encountering a piece of silicon material as a semiconductor, there's a probability that the electron will pass right through the silicon. There's a company in the Netherlands called ASML that is the collective brain trust for generating next generation semiconductors, next generation computer processors and such. They don't so much produce the commercial parts, they create the technologies and the machines that places like TSMC can then go spend billions to implement, or Intel or Samsung or whatever. ASML has working optically connected technology. So they've already proven it out. It's not at the consumer level yet, but it's within 1 or 2 chip generations away from being at the consumer level. Do you think they would do it if there was money to be made off of it? In other words, if I'm a Google and I have my AI data center and I've just spent $2 billion setting it up and getting it running, and I've got the power and I've got the water and I've got the building and I've installed all the computers and everything's running great, but my power bill every month is $3 million. If for less than $3 million a month in amortized assets, I can replace the entire array of computers by just replacing the main board of each of those computers, or maybe even the wafer assembly, take it out, swap in another one, and I can cut my power consumption by 25% on every one of those computers. Do you think I'm going to do it? Of course.
If it's less money to replace it than it is to pay for power, yeah, of course.
Yes, yes. And that's where they're at the moment. ASML is indicating that the waste heat reduction more than covers the cost of the next generation migration to go from copper to optical. Yes, look forward to a future where more things are based upon photons than electrons. Any more comments or questions before I stop recording? Hearing nothing.